Hey everyone, this is Alex, and this is the second installment of the Weekly Cheat. This week I want to talk about something which is called the Stern-Gerlach experiment. It's an experiment that kind of emphasizes some of the peculiar nature of quantum mechanics. So I'm going to be emphasizing that in the video today, but the reason I was thinking about this in the first place was we were talking about it in my quantum class, and we came up with kind of an interesting little thing that led us to be very confused. So hopefully I will have some time to talk about that, but otherwise I will just explain the basics of the Stern-Gerlach experiment. Okay, so what is the Stern-Gerlach experiment? So what it basically is it involves, you take like a hot box of atoms over here. So this is a box. And it has a little hole in it, and the atoms will fly out through here. And then you put them through a magnetic field that changes in space. So I'm going to draw it kind of like this. And the idea is that there's these B field lines. Oh, maybe I should put this in a different color. So red is for magnetic field. And so, just kind of for the sake of argument, I'm going to pick a particular B field. B field meaning magnetic field. And what happens is, as you shoot these atoms through this B field, the field will exert a force on it, and you have this detector screen on the other side. So I'll draw an eye over here to mean detector. And the question is, what do I see on this detector screen? So I think I have to go into the physics of these atoms a little bit more. So we know that not every atom, but for many types of atoms have this property called a magnetic dipole moment. And it comes from this thing called spin that I'm not going to talk a whole lot about besides the fact that it creates this magnetic moment. But let me just write this property over here. So the idea is that atoms have mu, which is a magnetic dipole moment. And this magnetic dipole moment is a vector that in 3 space it can point in any of the 3 spatial directions. And what ends up happening is, in a B field, this magnetic moment feels a force. And it has to be a B field that changes with space. So I'm going to actually put a little z over here. Oops, so I made a mistake there. But the idea is, if you have a B field that changes with space, then your magnetic dipole is going to feel a force, and I could show that, but I won't. Basically, the only thing that matters is that it feels a force. But let me show you exactly how it feels this force. So let me draw some sample magnetic moments down here, and what it would look like. So let's say this is our mu vector, and our field is pointing up and down. Then the force that I feel, which I'm going to draw in blue, is going to be in this direction, with a strength proportional to kind of the product of both the B field and the magnetic dipole. If I had a magnetic dipole that was pointing down, and I'm in the same B field, then my force is also going to point down. If my magnetic dipole is kind of pointing like at an angle to B, then my force is actually going to point still in either direction of B or the opposite direction of B, but it's a dot product, so let me write the equation. So the force is approximately, it's not exactly equal to this, but it's approximately equal to mu dot v, as far as we're concerned for the directions and stuff. So basically, it can only so it can only be pushed in kind of the direction of the B field or opposite the direction of the B field. You can't have it be pushing like parallel or perpendicularly to the B field. Okay, maybe let me just draw like one last example over here. If you had a dipole that was pointing this way, then you would have no force. Because obviously the dot product between them is 0, but you can imagine that since the dipole points perpendicularly to the direction of the B field doesn't have like any part of the magnetic moment that it can act on. Okay, so back to the actual experiment itself. So if you shoot a bunch of these atoms out of this box over here, these little, let me do it in a different color. These little magnetic dipole moment things, so each one of these arrows represents like a different atom. All of the atoms are actually going to be kind of randomly, their magnetic moments are going to be like pointing completely randomly, because that's just kind of how they start unless you have a reason to align them. So they'll be pointing in like all possible directions. And what you might expect if you pass this through the magnetic field over here is, one thing you might expect to see, based on the description that I've told you, is that, so let me write over here, classically. So based on the description that I just gave you, I think what you would expect to see is, so if this is my detector wall, you're going to expect to see something like this. And that's because, kind of on average, a lot more of the magnetic dipole is going to be pointing kind of like perpendicularly to the direction of the B field, rather than parallel to the direction of the B field. And kind of depending on how much of it is pointing parallel to the B field, it kind of gets pushed more. So most of them will be, most things will end up over here in the center. And then if you have it completely pointing down, it'll end up here at this end. And if you have it completely pointing up, it'll end up over here at this end. So it turns out that when you do this experiment, and they do it with silver atoms, you actually end up seeing something very strange, which is that instead of this like one continuous lump, you end up with one spot of atoms over here and one spot of atoms over here. And this is kind of like the original beam path coming in. So you actually get nothing in the center, and everything's either completely up, kind of in the same place, or completely down in the same place. And this is kind of, and they're kind of, let's see, I should say this 50% here and 50% here. And this is kind of really strange because, well, there's no reason that you should expect that things should feel exactly one of two forces, right? You can imagine, it's like saying that there's only two types of magnetic dipoles. There's the ones that point up over here, which end up going to this one. And then there's the magnetic dipoles that point down, which end up going only to this one. Yeah, and so that is actually what quantum mechanics predicts. And the reason is because what this machine over here is doing is it's actually making a measurement of the Z component of the magnetic field. So maybe another way I can write it over here is the force that is exerted on the dipole is equal to mu Z times Bz. And this mu Z over here is something that this measuring apparatus essentially is measuring. And when you measure things, you do this thing where you collapse them into, you collapse, any sort of particle into its eigenstates. In this case, there's kind of like an up eigenstate and a down eigenstate. So if you ever heard of like spin 1/2 particles, that's kind of what we're talking about. And the idea is basically when you do this measurement, even though the spins all started out completely random over here, they're all random over here, but as soon as you do the measurement, there's only 2 types of spins that are coming out. Ones that are up and ones that are down. Yeah, so that's the basic idea behind the Stern-Gerlach experiment. And so I'm going to continue now to talk about a little bit more advanced things, where I'm going to assume that you've already seen this before, just because I kind of want to. So, yeah, so I'm going to leave that apparatus up there, but I'm going to erase all this. So if you've seen the Stern-Gerlach experiment before, you know that on top of the fact that it's kind of weird that you only get these 2 bumps, the other weird thing that you can do is you can direct this magnetic field not just in the direction that I've denoted, which is Z, but you can also put it in like a different direction. So let me draw another picture. So let's say instead of doing that, and you're shooting the same kind of cloud of dipoles, instead of doing that, you end up, let's see, I'm really bad at drawing, but the basic idea is something like this. And then on this side, we have right, and the B field now is kind of pointing like into the page. Oops, I guess I should draw the arrows the other way. And so instead of in the Z direction, let's say that this is in the X direction. So B is equal to B naught X hat. And the basic idea now is that instead of being pushed up and down, these silver atoms are going to kind of be pushed into and out of the page. Right. Let's draw it like this. And what you're going to get is you're going to get a lump over here, which is like kind of into the page, and a lump over here, which is kind of out of the page. And this is in the X direction, and so the basic idea is that, whatever direction you direct this B field in, the atoms are going to separate along that direction. Okay? And, yeah, so that's what happens. You can direct this in a different direction, and I'm also going to say that you can also do it in the Y direction. Let's say you were able to bend this beam of atoms to like kind of go this way, and then you put another one of these magnets, kind of making it go left and right or something. Let's just say that that's another direction that you can push these atoms in, and it's going to have like kind of the same effect, right? So I'm going to, for the sake of making things easy to draw, instead of these gigantic magnets, which are really hard to draw, I'm just going to draw boxes. So my schematic is going to be, so here's my atom source. It's going through, and I'm just going to, instead of putting like this picture up here, I'm just going to draw a Z, which means that I'm separating the atoms along the Z direction. So I'm going to get exactly 2 beams coming out, right? One for the spin ups and one for the spin downs. And I'm going to do the same thing where I'm going to put an X here, which is, the thing that I just erased. It's separating it kind of into and out of the page now. And let's just say I block this beam off. So, one question is, what comes out of this beam? Is it going to be quantum mechanical, or is it going to be classical? And the answer is it's going to be quantum mechanical, of course. So you're going to get a lump, in the page and out of the page. So one thing you'll realize, though, is that these states over here have to be perpendicular to these states over here. The eigenstates that are coming out of the Z have to be perpendicular to the eigenstates coming out of the X. The reason is because over here we knew that these were 50% and 50%, and over here they were also 50% and also 50%. Yeah, and so if they had the same eigenstates, that means that you wouldn't have one of these, right? It would be like 100% one beam. So we know that there's two different eigenstates over here. And so the way we represent this, which you probably have seen before, is, so let's say that we denote our two eigenstates over here as vectors. So it's a 0, 1 and a 1, 0. And so you probably know that since this is perpendicular, you have to get some orthogonal components. So I'm going to call this SZ plus minus. Over here, I'm going to call this SX plus minus. And the SSX states have to be perpendicular to the SZ states. And so you can kind of construct this. It ends up being something like this. And maybe with like a normalization factor. Yeah, and so if you try taking the dot product between the SX states and the SZ states, you'll end up getting 0. So these are actually orthogonal. But on top of that, oops, that's supposed to be a Y. On top of that, if you do this thing where after you pass it through all of these, you pass it through a Y, you are still going to get like 50% and 50% again. And so that means your SY plus minus has to be orthogonal both to these SZ states and to these SX states. So if you're taking quantum mechanics, which I'm assuming you have right now, you probably know that you can use complex numbers, and so kind of the way around this is instead of having a 1, you can have an I. And so now if you do the dot product again, but you do the complex dot product where you conjugate one of the things you dot product by, you are still going to get 0, right? And so that's kind of cool. Yeah, and so here's the question that we were trying to consider. So assume that you're in like 4 spatial dimensions where you have W, X, Y, and Z. So we kind of were able to get 3 spatial dimensions because we had, we had our original states, we were able to find an orthogonal to it in the real numbers, and then we were able to find something orthogonal to it in the complex numbers. But you actually can't get another set of complex states like this, as far as I can tell. And so what happens if you add this other dimension? Yeah, so I think I have an answer to this, but in the interest of time and finishing the rest of my homework for this weekend, I think I'm going to leave that for another time, and you guys can ruminate about that. And I don't think I was very clear about what the problem was, so if you're confused about this and want to figure it out, you can shoot me a line and I'll try and explain it to you better, or put up another video explaining all of this better. But anyway, the basic thing is that there's this experiment, the Stern-Gerlach experiment. It involves pushing atoms with a magnetic field. And instead of getting this classical, like kind of lump over here, you end up getting this very quantum mechanical discretized states. And the Q in QM stands for quantum, and quantum just means kind of like a discrete unit of things. And so you can see that instead of this kind of spread out, set of particles, we end up getting this very discrete set of particles. And the fact that things are quantized is, just kind of interesting and underlies, all of this is actually underlying everything that's going around us every day. And one interesting thing you might wonder is how do you get from these quantum things to kind of our real world, where everything is kind of continuous, and that's something that I will actually probably talk about another time. Yeah, but that's it for today.